This video is intended to be a visual tour of some selected elements of data management. This slide illustrates a typical data set that would be used in a learning health application. There's one row per patient. In other words, the unit of aggregation is the patient. Patient is also thus an ID variable. There are multiple columns, typically called fields or variables. Each field has a data type. For example, sex is a character field with two possible values, systolic blood pressures are a numeric field, and so forth. Hypertension is a derived variable. That is, it's derived from systolic and diastolic blood pressure using a formula. Large databases tend not to store derived fields. For example, a large database would probably contain systolic and diastolic blood pressure, but not hypertension. Moreover, large databases try not to store multiple copies of anything. For example, a well-designed database won't have the same information about hypertension in 50 places, but instead will keep it in one place with directions for how to access it. On the other hand, if you're creating an analysis file, that is, a file that will be an input to a statistical analysis, you probably won't worry about redundancy, and instead will want to amass as many variables in one place as you can. Associated with the database is information about that database, called meta-documentation. An example is a data dictionary, illustrated here. The rows of the data dictionary are the variables. The columns contain information about those variables. For example, their type, possible values, labels, and so forth. I'll now illustrate some data management functions. A simple such function is taking a subset, for example, selecting all the males or all the females. Please note that the new data set could potentially use two variables for its ID, depending upon the context. The record number starts with 1 and is the row number in the new data set. The other identifier would use the original patient ID. This would allow us to link back to patient characteristics from other databases. Stacking combines data sets vertically. For example, in a multi-site study, data originally collected within each site separately and then combined into a single analysis data set. The ideal is to have identical variables. Otherwise, these variables will be systematically missing. And this is illustrated here with Z for site 1 and Y for site 2. Having identical variable names and codes also simplifies the process. Otherwise, time and effort will be required to produce a crosswalk. Potential problem with stacked databases is someone might be labeled patient number 1 in both datasets. One way around this problem is to use the row number from the new database. Another is to make a new ID variable that uses both site and patient number within site. In a merge, sometimes called a join, the datasets in question contain different information on the same sets of patients. Implicitly, this only works if the datasets in patient have been sorted by the same ID variable, although in practice an actual sort isn't necessarily required. If the lists of patients aren't identical, then missing values will be induced, as illustrated here. Sometimes it's useful to keep track of whether missing values in a data set are created by this process, which makes them structural missing values, or whether the information was solicited and the answer was somehow missing. Things become even more complicated with many-to-one merges, and they get out of hand entirely with many-to-many merges. This slide illustrates a many-to-one merge. A visit-level data set has one record per hospitalization, while a demographic data set has one record per patient. The many-to-one merge attaches gender to each hospitalization. This illustrates a restructuring, whereby a hospital-level data set is translated into a database with one record per patient. There's a potential for lots of white space within this database. For example, if one patient has 20 hospitalizations but no one else has more than 3, then values for hospitalization 4 through 20 will be missing for every patient but one. The same process can work in reverse. This illustrates a roll-up. For example, the input has one record per hospitalization per patient, and the output file has the total length of stay with each patient. This sort of information that's often rolled up includes counts of events, total charges, whether an event has occurred ever for a patient, and so forth. Some takeaway messages from this video include the following. Within clinical databases, data aren't always stored in a natural format for analysis. Instead, they're stored in order to conserve space and avoid redundancy. The first thing you'll typically do with a clinical database is extract a flat file containing a subset of records and a subset of variables. The most important variables to pay attention to are the ID variables. Software tools can restructure a database in any imaginable fashion. You'll know enough to interact with a programmer if you can diagram the flow of data, as illustrated in this video. And finally, standardization can simplify your life.